Today we're going to be talking about the definite integral. And if you remember yesterday's lesson, what we did was we looked at drawing in rectangles to estimate the area under a curve. So we drew in all these different rectangles to help us estimate the area under the curve. And what we did is we said eventually that this was a sequence that we could eventually add in the height, or the width, I apologize, the width times whatever the height was. And remember, our height is that function value. Our heights were each one of our function values. And that's where our sequence, or the sum of our sequence, came from, is that it was a sum of a bunch of different heights. So, area is a sum. It's a sigma notation. It's a sigma notation where this delta x was standing for our width. And we were summing together our function values that were standing for our height. Now, what's important for you guys to understand is what if we now express this as a sum of limits? Meaning, what if each one of these widths got smaller and smaller and smaller? Or I had an infinite limit. So let's break down this infinite limit that we have here. What if we now have, well, this last part again, remember, that's our width. But what if this was those limits, those all-important limits, the first thing we really learned in calculus? And that's a limit as the number of rectangles went to infinity, which means each one of these widths is going to get smaller and smaller and smaller. And what do we get when we get that? We get the area under the curve, or our all-important integral. So when we take the limit as of a sequence here of this sum where n gets bigger and bigger and bigger, making our width smaller and smaller and smaller, we get this notation. This notation is super important to us. Okay? That means the integral from a to b, where a is less than b, of f of x dx. Dx, remember, is standing for the width, or it's telling us which variable we're taking the integral with respect to. Okay? Meaning that I'm taking the integral, or I'm finding the area back to the x-axis. Okay, that's what that dx tells me. Okay, so some important key terms. You have the lower limit. Okay, this is the smaller of the two numbers, which is a. And then you have the upper limit, which is the larger of the two numbers. It tells you the interval that you're finding the area of. You have your function, the integral sign. It looks like an elongated S, doesn't it? Because we're finding the sum. Dx is the variable of integration, and f of x is the integrand. So again, remember that this means the area under the curve from a to b. Okay, breaking this down. So the interval from -2 to 5 is partitioned into n subintervals of equal length, because remember on the top we did b minus a, so that's 7 divided by n, the number of rectangles we're going to have. M sub k is denoting the midpoint, so we're doing a midpoint approximation. Express the following as an integral. So basically, what does this mean in terms of our integral? Well, remember, this is our a, this is our b. So -2 is the a, 5 is the b. And we're going to take this of some function dx. Now remember, what are we doing? We're plugging in some value there for m sub k. Okay, we're plugging in all of our different values of our curve. What's our curve? 7x squared minus 4x plus 8. And let's put that guy in parentheses. Okay, so that's what this whole limit here means. It means that I'm finding the area under the curve of that function from -2 to 5. And as we work through the chapter, I'm going to be showing you guys some tricks. By the end of the chapter, you should be able to find this area under the curve without a calculator. And I'm going to be showing you guys. That's basically our goal of this chapter. But first, let's just start out with some basic integrals. So evaluating that integral. Remember, it means area under the curve from -3 to 5. Well, what does that curve look like? So it's a line with a slope of 1. So that's what our curve looks like. Now, what am I finding when I'm finding this integral? I'm finding from -3 all the way over to 5. I'm finding the area of this geometric figure. And it's important that you understand that, hey, that's a geometric figure that we can find the area of. What is that? That's a trapezoid. What's the area of a trapezoid? That's 1/2 base 1 plus base 2 times the height. Okay? The height, the bases, remember, the two parallel pieces. So that's one base. One of the bases has a value of 2. The other base is the side that's parallel to that. That has a value of 10. Now our height is that distance right there, which is going to be 8. So now finding that area ends up being 48. So for right now, we're just using and looking at this like a geometric figure. Eventually, I'm going to give you guys a formula to help you find the area under the curve. But for right now, let's just look at them as geometric areas. Okay. Okay, next one, evaluate the integral. The integral of 487 dx. Remember that this is a function. This is some f of x equals 487. Well, what does that look like? That's a line all the way up here, and y equals 487. And I'm going from -2 to 7. So, what type of figure is that? That's a rectangle. Okay, what's my width? My width is 7 minus a -2 times by my height, which is 487. So what does that end up being? That ends up being 4,383. But now let's come to some sort of conclusion. Therefore, the area under the curve from A to B of C of x, where C is some constant, is that constant times by B minus A. And that is super interesting. Okay, that's building on what we're going to be learning here, and that's going to really help us in a few days. Okay, next example. Okay, so you have to analyze what type of figure you have. This is a circle. That's actually a semicircle with a radius of 4 shifted up 3 units. So a circle of radius 4 shifted up 3 units. And my center is actually at the origin, so I was off on one of those. So I have really two pieces here. I have this bottom piece, which is a rectangle, and then I have a circle that's of a radius of 4. So we have two pieces that we're going to find the area of. This bottom piece, well, that's easy, okay? That's going to be the area of a rectangle. My height is 3. My width, or this whole width, is going to be 8. So that's equal to 24. Now the top piece, that's half of a circle, pi r squared. Our radius was 4. So 4 squared is 16, divided by 2 is 8. So the area under our curve, or what this integral is going to evaluate to be, is 24 plus 8 pi. Okay, sometimes they're going to give you the following information: the area under the curve from 0 to pi. Now look at what they give us from negative pi to pi, that the area here, so this shaded region, is 2 units. Find each of the following. So our first example, we're finding from pi to 2 pi. Let's look at what our sine curve looks like under one rotation. So this is 0 to pi. Halfway in between, you have another x-intercept, which is at pi. So what they're giving us is they're giving us that this area right here is 2. What do you know about this area that's above the curve and the area that's below the curve? Those two pieces are going to be essentially congruent. Just remember, area below the curve is negative. So this area above is the same as the area below, just negative. So our area below the curve is going to be negative 2. Okay, the next example. Well, what did we do for the last piece? What we did for the last piece is basically we're going to adjust this area up 2 units. So from 0 to pi, I'm going to shift my curve up 2 units. So my curve is going to look something like that, and it's a super elongated version of it. Now remember, this is 2 units. I shifted this up 2 units. So what's the area of this? The width times my height is 2 pi. So my total area is 2 plus 2 pi. Okay, this last slide, please make sure you write this down. This is and I know it says 6.3, but I like to throw this in as fast as we can. So, order of integration. So, if the smaller number is on top of the bigger number, okay, remember always A is a smaller number, you can flip their order and make the integral negative. Basically, you're just going in the reverse direction. You can think about it that way. What's the area under the curve from A to A? That's nowhere. Okay, you haven't gone anywhere. What you can do is you can sometimes pull out a constant. That's going to make your life easier sometimes. And if there's a negative, you can pull the negative out, and A and B don't switch. So basically you can pull a constant out, kind of like with derivatives. When you're taking the integral, you can take each term and break it down like we could with derivatives under addition or subtraction. And then what we can do also is if you could split up your curve from A to B and then B to C. Okay, if you have 3 different points that you want to find the area of, That's going to be the sum of the areas going along your x-axis. Okay? Notice how there was no product or sum formula. Okay? That's going to be a challenge that we're going to have to deal with when we start really getting into integrals. That's it for today. Please make sure your lesson summary is submitted on time.